So this talk will be talking about the state-of-the-art machine learning algorithms or models for tabular data. Um, so just a quick blurb on me. I'm a Kaggle Grandmaster. I've spent way too much time on that website, and I've done a whole bunch of different competitions. And I've done well in some competitions, but I think my main contribution has been just writing a whole bunch and being thorough of my exploration and discussion of some problems. So my initial story, I'm self-taught. I went to college for business, and then I transferred to uh, programming and machine learning and all of that just because I thought it was really fascinating. So anyone who's intimidating of trying to make that dive, I'm one of the few examples of someone who's made it out the other end. If you stick with it, it's definitely possible. Um, right now I'm working at H2O, and so this is kind of our bread and butter at H2O is really good handling of tabular data. We do automatic machine learning, so we do all of the stuff that we just discussed in the previous session, XGBoost, LightGBM, different variants and handling features and stuff like that. Right now, I've been working mostly on document understanding tasks, but I still have done quite a bit on tabular data with our driverless AI software. And I work with a whole bunch of people who are completely experts. There are a lot of the people who are famous on Kaggle for their competition wins and the way that they've handled tabular data in the past. So just an outline of the talk. I'm going to explain what is tabular data. It might be obvious to some, but I still want to lay that out and show exactly what we're talking about and what problem this discussion is going to be relevant to. I'll talk about what you might predict. I'll talk about some special cases of tabular data, and then I'll get into the gradient boosting decision trees, which is the main algorithm that we'll be focusing on. I'll talk about some of the different implementations that are available. I'll talk about how they perform and a little bit of comparison between them. And then after that, I'll talk about preparing the data, which is one of the more important aspects. The algorithms are great. These are state-of-the-art algorithms that will get you great performance, but you still have to put a little bit of work in to get the most out of them most of the time. So we'll talk a little bit about handling missing values and also different transformations that you might apply that can give you additional predictive power. So starting us off with tabular data, when you think of tabular data, you should be thinking about typically spreadsheets and databases. So anytime you have something at work and they have a database that has a whole bunch of information in it, it's got a bunch of rows and a bunch of columns, that's the kind of thing that we're thinking about. And very often with these, you can have mixed types of data. So tabular data isn't necessarily all numerical or categories or something like that. It can be more complicated. So like, for example, this on the screenshot I have here is from the Titanic data set. And this is kind of one of the benchmark simple tabular data sets that everyone goes against. And you can see that there's all kinds of different stuff going on. So there's ID numbers, there's a stat of whether they survived or not, there's the P class, there's the name, so that's some text that you have in there. There's sex, which is represented as text, but would probably be represented as categorical in a model. There's age, there's all kinds of stuff like that. So you might end up with a whole mix of numerical, categorical, dates, text, a lot of stuff that you might want to extract some information from and pass to your model. So talking a little bit about the special cases, it's simple if you just have a spreadsheet, someone just gives you a CSV or an Excel file, or you just take a dump from a database. But it's slightly more complicated if you have stuff that is in a time series format or something else. So it's possible to treat these as tabular problems, but people don't typically think of them in that way. So if you have stock prices, you can treat that as tabular. You can say, here's all of the different stock prices. Let's try to predict them tomorrow. But typically you would introduce some alternate methods to handle them slightly differently. So that's not necessarily what we'll be focusing on, but you can treat these as tabular problems. So examples of that: stock prices, weather, etc. Lots of different sensor data. There's different ways that can go. And then another thing is sometimes the data requires aggregation. So if you have something in a database, you might have a whole bunch of different tables and you have to find some way to merge them together and combine that information. So for example, you might have a whole bunch of individual transactions and that might map to a whole bunch of different customers. And to do anything interesting with that, you have to group by the customer to get something useful, because the individual rows of data on their own might not actually be that interesting. But in combination, you can get an interesting tabular data set out of that. So then moving on to gradient boosted decision trees. We've talked about decision trees with the book club, and we also just talked about these this week in the previous session. So the gist of these is they're very, very strong models. Most people use them as their default, and very often you don't progress beyond these in terms of accuracy. And the key algorithmic detail is you're growing decision trees in a directed manner. So your successive trees are learning from the errors of your previous trees. So you train one decision tree, and that first decision tree is trying to just model the data. And then your next one is trying to model the error of the first tree's predictions, and so on. And so, for example, if you have 49 trees, you've trained 49 up to that point. Then the next one is looking at the errors of the sum of all of the previous trees and then training a 50th to try to correct for that error. So one of the major things with gradient boosted decision trees is that the decision trees themselves have a strong capacity to overfit. We've talked about that in previous chapters discussions. If you have a single decision tree and you give it infinite depth, it can just draw a box around every single sample in your data set and get you the right prediction on your training set, but it might have no use on your validation set or unseen data. So you need to find some way to regularize this pretty heavily, because you're doing lots of these decision trees stacked on top of each other. So one of the key things that people typically mention with gradient boosted decision trees is you're doing an ensemble of weak learners. So in this case, you don't want your individual tree to necessarily try to learn all of the data. You just want to learn part of it, and then the sum of it will be what's powerful at actually making the prediction. So talking about, let me actually open this page and just show this. So there's a bunch of different implementations of gradient boosted decision trees. And if you look at them, all of them will have a whole ton of parameters. So this is the one for light GBM. If you just scroll through this, there's piles and piles of parameters. So figuring out what exactly is useful and what is important is somewhat difficult, and comes with a bit of experience and just studying from what other people have done, because there's lots of different stuff that you can get lost in if you haven't worked with them before. You won't know what's significant. So talking about these regularization steps, some of them are similar to what you use for just regular decision trees, but then others are gradient boosted decision tree specific. So this is just my opinion. So take that with a grain of salt. But my opinion, when you're looking at these, the ones that you should be tuning that are decision tree specific, is mostly just the depth. That's going to be the thing that drives the most change in your performance. You can try tuning all of the sliders and you'll see some movement in performance, but the depth is really the thing that will make the biggest difference if you actually toy with the various knobs. And then of the ones that are gradient boosted decision tree specific, the ones that I always look at are the bagging fraction, which is how much of the data is actually sampled with every tree, or depending on if that iteration was bagged or not. And basically what this is doing, in my mind at least, is you have a data set, imagine it has 100,000 rows, for example, and then you have your bagging fraction set to 80%. It will take 80% of the data and then discard 20% of the data and then train a tree upon that subset. And this is useful because you might have various different outliers within your data set, or you might have stuff that causes some amount of noise. And so training on these new subsets makes it much more robust to things like that. And then similar with the feature fraction, that's another parameter that you tune, and you can say, I have 100 features, give me 80% feature fraction, and then that will pull in 80 of the features instead of 100 for the trees. And this is also useful for similar reasons where you don't want to fit too strongly to one specific feature. So if you have one feature that's really, really strong, and it's chosen as the first decision split in all of your trees, then you don't have a lot of varied trees. And so this is one way of forcing the model to take alternate splits and try different things, and it ends up with a much more robust model. There is a discussion in the previous talk of whether feature fraction was really that important. And I would say that it's pretty much always useful unless you have a very, very low number of features. Like they were talking about 12. I think even with 12, I would say having a feature fraction of 80 or 90 is probably reasonable, just to make sure that you're not completely fitting to one feature that's very predictive and not giving the rest of the features enough time of day. And then another thing is the bagging frequency. And so this is basically how many iterations before you do bagging, or how often you do bagging. So if you have it set to 3, every third tree will be bagged. But frequently this would be pretty much always you would do bagging on almost every tree. So along with this, I wanted to show some visualization of a gradient boosted decision tree. And I've shown this in the past. I don't know if anyone else has seen this. I'll copy it over into the chat. So basically what this visualization is doing, it's a little interactive dashboard where what you get to do is try various different data sets, and then you can see the decision boundaries of the individual trees. And then you also get to tune some of the parameters and see how that affects performance. So for example, if we do tree depth of 1, then it's only able to make one decision per tree. And we can actually visualize the different splits that it's applying at each decision, or at each tree rather. So with tree depth 1, we can see that all of these decisions are just individual splits. It's saying when X is above this value, it's one class. When X is below this value, it's another class. And we turn the depth up and we see that the decisions become much more complicated. It does this sort of jagged pattern and has lots of different splits around it. And then the subsample, this is subsample of the data. So this in my presentation terms would be the bagging fraction. Depending on who you talk to, it will be called different things. So sometimes it's called bagging fraction, sometimes it's called subsample. And so you can play with the subsample and you can see as it changes how much it's sampling the data, it will also change the performance. And then another thing is the number of trees. So as you fit more and more trees stacked on top of each other, your training loss will go down because you're learning from those values. But your test loss, it just depends. You can begin overfitting, or you can not have enough trees and you haven't fit properly yet. So you can add additional trees, and you can see that the training loss went down and the test loss also went down accordingly. Any questions or thoughts to this point? Small challenge out there to anyone who can try to fiddle with these parameters and get a lower test loss than me on this data set. If anyone wants something to play with.
What loss did you get?
The test loss is 0.107, but it also depends on which data set you pick.
So you're doing it on the fourth one, and
Mm-hmm.
cool. And you only got, looks like you only got like 2 points wrong.
Mm-hmm. Yeah. And so one of the cool things is it also shows us the decision boundaries of the original trees. So this is showing this tree made this decision on all of these. And then if you hover the pluses, it actually shows you the summation up to that point. So this is the everything up to the 15th tree added together. And then if you hover just a box, it will show you the decision boundary of that specific tree. So that's just a fun thing I like to show sometimes, because I think it shows the additive process. I'm not sure what this is made in, honestly. It might
That
be.
looks, I was going to say that's like a faster version of grid search.
Yeah, to an extent. This is just a very simple data set, so you can actually mess with the sliders. But I think it would be a little bit harder if you were doing a larger data set, because every time it does this, it has to train a new model, basically, or they've cached a subset of the possible combinations.
It's a lot different than grid search because you're doing an intentional change in a parameter at each step, whereas in grid search, you're just blindly searching all the possibilities that you can think of and put in a grid.
Hey, Ryan, I'm noticing for the purpose of a visualization, you want to see the different trees adding together. And so the learning rate there they have is 35% or whatever, 0.35, 0.36, I can't see quite that well. But do you know what the default is? I think the learning rate typically defaults to a smaller number than that, right?
Yeah, it's typically a lower value. The default out of the default is 0.1.
Yeah, I just thought I'd point that out because for the visualization, it makes sense. You want to use slightly higher numbers so you can see them getting added together without needing 1,000 or 10,000 trees. But I didn't want anyone to get confused to think that that actually is a common practice to use such a high learning rate.
In practice, we do actually use relatively high learning rates. I wouldn't think it would be unreasonable to use 0.35 or 0.5 or something like that. But it also just depends on how many trees you're stacking together. So the learning rate in our software in driverless favors large learning rates because it means you have to fit less trees and you can iterate faster and try more combinations of features and stuff like that. Because very often what you'll see actually is the difference between a 0.1 learning rate and 200 trees and a 1 learning rate and 20 trees is not that drastic necessarily. So we tend to do a higher learning rate and less trees. But if you are trying to scrape as much performance as possible, typically you'll do slightly lower learning rate and more trees.
Awesome. Thanks, Ryan.
Yeah. So this is the visualization that I just ran through. So there's multiple different variants. There's even one that I forgot that was mentioned in the previous talk. There's XGBoost. Yeah, Ian called out the one I missed. So there's also Cat Boost, but I have a joke about Cat Boost I'll tell later. So there's XGBoost, and I was talking about it in our breakout rooms earlier. XGBoost seems to be very popular still, but my general opinion, my default is LightGBM, because it almost always gets me better performance, and then it also trains much faster. So I tend towards LightGBM, but a lot of people really like XGBoost, and it seems to still be a lot of people's favorite. I tend to prefer LightGBM, but in almost every case, if you are truly trying to squeak as much performance as possible, doing some sort of ensemble between the two, so taking output from both, then averaging them or blending or stacking or something like that ends up getting you better performance doing both in tandem rather than just one or the other. So another one that is available is from sklearn. So they have their gradient boosting regressor classifier. My general opinion is just never use that one. It's not as good as the other stuff that's available. I don't think it handles missing values, and it's significantly slower than everything else. So one of the things that has been released recently is their HIST gradient boosting regressor, and that one functions more closely to LightGBM, so it's way faster, and it's also able to handle missing values and categoricals and stuff like that. So my recommendation is, if you are looking at using scikit-learn models, to use the HIST gradient boosting regressor or classifier, depending on what your problem is. And then, as Ian mentioned, so yeah, for Ian's question, HIST gradient boosting is now in the main 1.0 release, I believe. There was a period where it was experimental. So if you were on 0.9, I believe, you had to do a certain command to enable it because it was still marked as experimental. But in 1.0 now, it's in the official release, so you don't have to do anything to activate it. So the other thing Ian called out was there's also Cat Boost, and that one I have less experience with. And the joke that my coworkers always tell is that you need to know Russian to be able to operate it properly, because for whatever reason, it comes from Yandex, which is this Russian company, and a lot of their documentation seems to favor Russian still. There is English, but it seems like mostly just the Russians prefer it, and then they know how to operate it well, and most of us don't really use it. But
that's fantastic. I was looking for something English which is written by Russians. Thank you very much for this.
Yeah, I'm glad that's useful. But we have certain Russian people in our company, and they're successful with it, but I've never really used it. In my experience, using XGBoost and LightGBM will get you pretty much all the way to the most accurate solution you'll get. Some people do stack an additional Cat Boost on top of it, and then they get a little bit more. I think the main Cat Boost contribution to this whole gradient boosted decision tree ecosystem, though, was its handling of categorical features, which is supposed to be better than the other variants. I haven't personally used it, so I can't speak to its usefulness. So just pulling some benchmarks, these are directly out of their respective papers. So this is the top one is from the XGBoost paper, and it's looking at its test area under the curve. So in that case, higher is better. And so you can see that the XGBoost, its AUC is marginally better than scikit-learn. I would say not even worth noting. But the big thing is that it's so much faster. So this is them comparing the gradient boosting classifier. And this is exactly what I was saying, is you should pretty much always be using XGBoost or LightGBM or scikit-learn's own HISS gradient regressor, because the original gradient boosted regressor is so much slower. It's an order of magnitude slower. So then since LightGBM came out after XGBoost, they also have some comparisons against XGBoost. So this is looking at various different data sets. And then it's also looking at the time it takes to train. So that's what this left graph is. It's saying the time per tree to do training. So if we look across the row, XGBoost has 2 different modes. It actually has more than that, but let's just say they have 2 modes for now. They also have a GPU mode that's different. And their main modes are exact and hist, or for histogram. And so you can see that their histogram mode is much faster. It's 4 times faster, basically. But if we compare it to LightGBM is even faster than that. So you can train more trees more quickly, and you can iterate on experimentation and stuff like that. And then looking at the performance of it, you can see that LightGBM, on the left, we saw it so much faster, but then at the same time, we can see that it performs exactly the same, if not better, across all of these different benchmark data sets. So for example, on the flight delay, we see that the XGBoost histogram method basically exactly matches the LightGBM method. For this data set, it gets actually slightly better on the LightGBM. And that's been my experience pretty often, is LightGBM ends up being the fastest and the best in terms of performance. So if people are doing individual models, I recommend LightGBM as their starting place. So I'll pause here if we have any questions before I talk about preparing the data.
I think you pretty much already mentioned it, that, you go with LightGBM as your go-to. Would you say, like, if you can give like a proportion of how many times, what's the proportion that you just naturally gravitate towards that model and it tends to be the better performing model out of anything else that's out there?
So LightGBM is just my default at this point. That's always what I try if I'm doing something. And typically I only bring XGBoost out if I am trying to squeeze a little bit more, and I will use the XGBoost as sort of an auxiliary, like additional boost, because I know that almost every single time I've taken the 2 models and then I just average them together or give them a weighted average, and then I end up with a better ensemble with those 2 together. But I very rarely at this point use XGBoost on its own. I have almost never seen it be the winner. I've never said this XGBoost model is so much better than a LightGBM model that I'm going to just discard the LightGBM. Does that answer your question?
Oh, yes. Thanks.
Great.
Ryan, so if I understand correctly, you don't do you even bother using like a random forest, or?
I personally don't. I have seen the gradient boosted decision trees beat random forests enough to this point that I don't even try them anymore. But it really depends on the size of your data. So one of the things that they mention in the book was that it's much faster beyond like 10,000 rows or something like that. My hunch is that on slightly smaller data, I think the random forest and the extra trees and stuff like that will be competitive. But I think as you get to bigger and bigger data, the sort of directed learning from the gradient boosting ends up making it learn a better model. So I don't really use random forest very often, but if I ran into some smaller data set, I might consider bringing it out again.
Got it. Thank you.
A bit unrelated. There is a method which is called C5 period 0, and it is a tree-based method. And it is as far as I know, it is still protected by copyright, and people do not know what exactly they do for the methods. It is faster than usual CART or whatever usual decision tree method, which is used in R and Python, but it is not quite known, as far as I know, what exactly they use. Do they use, entropy? Do they use Gini? What they use? You can see the tree when it is constructed. So it is about what you said, that for extreme, well, these two methods, which looks like they use different ways of tree construction. So I was wondering what other tree constructions of tree exist besides the usual, I mean, what kind of division I use for construction theory of trees, because I haven't heard about anything else besides the standards.
Yeah, I haven't dug into that too much, so I don't know that I can really speak to that. I know that the splitting method between XGBoost and LightGBM is the actual like main differentiator. So my loose interpretation from the LightGBM stuff is that it actually puts things into predefined bins. So I believe it does like 256 bins by default or something like that. And then it makes it so it doesn't have to sort the whole data set and calculate for all of the splits. So it only does it for 256 rather than just however many unique values there are. And I think that that also functions as some form of regularization, because it doesn't have that precision to mark every single split in between all of the points. But I'm not super familiar with all of the different techniques. I haven't dug into that much depth really. Any more questions? All right, so moving on to the section preparing the data. So I mentioned at the beginning of the talk, the XGBoost, LightGBM, all of them will do a phenomenal job, but you still have to do some amount of preparation of the data before you pass it to them. They can do certain things and handle missing values and stuff like that for you, but you still generally want to look at the data and then make some decisions to try to make it as informational as possible for your model. So the main goals that you want is you want to preserve as much original information as possible. So there's various different things that you can do to transform the features, and you want to keep the original information so your model is actually what's learning rather than doing anything destructive to it. You don't want to lose information before you pass it to the model, because that could be something useful for the model to learn from. And then the other thing is you're trying to transform the data in the most learnable format. So there might be something that is nearly equivalent, but it might actually take more splits from a decision tree or something like that. So you want to make sure that you're formatting it in such a way that it is able to learn it, and it also generalizes. So I'll talk about some cases of that after this. So in the case of gradient boosted decision trees, the scaling actually doesn't matter. So if we were talking about neural networks or some other algorithms, the scaling would matter. So if your value was between 0 and 100 versus 0 and 1000, that would actually make an algorithmic difference. But in the scheme of gradient boosted decision trees, that actually doesn't really matter. So we won't talk about that really. So the first thing that I'll talk about is just handling missing values. So like I was saying, with gradient boosted decision trees, depending on the implementation you use, it actually doesn't matter. You can just pass them in and you can just say this was a missing value, and then it will just handle it as a missing value, and it won't mess up your predictions or anything. But if you're doing certain implementations, they will actually require you to insert values and fill in the blanks, basically. And it's also important if you're doing stuff with neural networks. So how you fill in the blanks can actually be very informative, because sometimes you might want to represent the algorithm. I am filling in a value, but it's also not a real value. So sometimes you might just, like with gradient boosted decision trees, it's pretty reasonable to actually say, just do a random number that is outside of our normal range. So if you have, for example, like an input to your model is square footage or something like that, you could just pass it -999 or something like that, and it would be perfectly reasonable to do that, because it just takes a single split for the model to say, okay, this is -999, and it doesn't overlap with any of the real values, and now it can just understand this isn't actually the square footage, it's just a missing value, and then it can treat that split as such on the decision tree. If you're doing neural networks, which we're not really focused on right now, but I just wanted to point out, it's pretty reasonable to try to fill in with the mean or the median for that column, because you need to actually impute some reasonable value that doesn't screw up the neurons of the neural network. So that's the handling of missing values. For some algorithms, it matters. For some algorithms, it doesn't really work. So talking about the feature transformations, this is what I was mentioning earlier. Sometimes you can just reformat something and it ends up being way more information dense. Pretty much always a gradient boosted decision tree with enough trees can represent something. But if you can take something and it used to take 100 trees to represent, and then you transform it to a different format, and then now it makes it so it only takes one tree to capture the information that you were trying to learn, then it will end up making you a more generalizable model. So I would say generally the best step is just to start with the raw features and just pass that to the model and see how it does, and then actually take a look at the data and understand maybe there's something that you can represent in a slightly better way. So one of the examples of this is target encoding. This is something that we see successful in a lot of different use cases. So the example I always use is, imagine that you have some eBay listings and there's a whole bunch of different categories that they have. So they have all stuff ranging from little trinkets all the way up to cars. And you know that all of these different categories have entirely different mean prices. So a car might be 20,000 and a little keychain might be 99 cents on average. And so you can give the model the raw category ID numbers. You can tell it, this is a car, this is a small trinket, this is, I don't know, whatever else. And it can try to learn that pattern, but a much more information dense version of that would be target encoding, which would be basically saying, okay, the average car is worth 20,000, for example, and the average trinket is worth 99 cents. And so that gives your model a calibration point to basically base its splits off of. And it's much better than just giving it an ID number and then making it try to learn that interaction all by itself. So there's target encoding is just one example. There's lots of different things that you can do. Within driverless, one of our big things is that we have all of these transformations that we've accumulated from all of the different Kaggle competitions. So we have different transformations for numeric data, categorical data, time series, NLP, etc. And so we have this list of all of these different things, and these are the various different reformattings that you can have with this data that when we run driverless, it actually tries out a bunch of different combinations of these and tries to get you the most information dense version that ends up getting you the best prediction power. So another thing to think about, I'm reading this question in the chat. Does target encoding mean the feature instead of being category ID is, yeah. So basically you would swap out the category ID, and instead of it being entered in as the trinket ID, which could be 1 or 17 or some random number, you would replace it with the average price. So it could be like 99 cents, or it could be 20,000 in the case of a car, or something more expensive. And that gives you a much more information dense version. And you can also do that not necessarily on your target. So if you were trying to predict the price of something, then the price might be a useful starting point. But if you were doing something else, you can also target encode based on other variables, for example. So if you have zip code, for example, you can replace zip code with the population of that zip code, or per capita income, or a whole bunch of different things. And so it's not necessarily target encoding, but you're encoding it to have some actual numerical relevance, whereas zip code on its own might not actually tell you a whole lot.
Hey, Ryan, if I could just jump in to clarify. So when you target encode, you potentially have some sort of collisions, right? Like maybe the average, if you're doing eBay categories, the average cost of a, I don't know, a jacket is similar to the average cost of a, you know, something else. And so in theory, you're losing some information because those two can collide, and then you can't really tell them apart.
Mm-hmm.
But what you're pointing out is that you may gain a whole lot more than you lose, because that representation is just so much informative, where instead of having category ID 1, 2, 3, 4, 5, 6, 7, 8, 9 that are, it has to learn. It's so meaningless. Instead, it would have category, I don't know what you want to call it, category target encoded says 99 cents, $50, $20,000, $50, whatever.
I don't think you're losing anything if it's because it's taking your target variable value. And if the target variable value is the same for both categories, then there's no information about in that, just that individual isolated categorical variable, any information at all about your target variable that isn't shared between those two categories. Those two categories are equivalent in terms of their effect.
Yeah, that's a good point. I mean, it's possible that they're not really completely equivalent. Like, right, their means might be equivalent, but they may actually have different distributions or whatever.
Yeah,
And then
yeah.
Ryan was mentioning you can target encode on something different. So hypothetically, you could be trying to predict income, but you target encode zip code by population. And so then again, any two cities that are the same population, they become indistinguishable when you target encode them.
Oh yeah.
But it's all about the pros outweigh the cons.
Right, and you're just adding that as an additional feature above all the other encodings you're doing for that categorical variable. You're not discarding the other information in the categorical variable unless you actually want to, unless you want to do dimension reduction. There's no reason to not do target encoding on both population and do it on the feature encoding on the population and then target encoding on the target variable. And you can even do that for combinations of categories if you're worried about the stuff you're talking about where the distributions are different and the mean is not the most important thing, like the combination of zip code and neighborhood, or zip code and whatever city name, and you could have that pair be a category and then target encode that or feature encode that.
Cool. Thanks.
Mhm.
Thanks, Hobbs.
So another example I wanted to bring forward is, this is something I actually ran into in some sensor data when I was working at my old company, is a decision tree is really good at drawing the boundaries around certain things. So it's saying if it's greater than this value or it's lower than this value, but it's not necessarily phenomenal at just understanding the actual underlying pattern. So we had some data one time where basically all of the actual integer values were the real readings. And then if something showed up as like 1.6 or 1.73 or something like that, it was a value that actually meant something else rather than the actual integer. And so the model actually can't learn that very easily, because if you have something that's 1.6, 2.6, 3.6, it's hard for the model to actually learn every time there's a decimal point value that should be treated differently than something that is 1, 2, 3, 4, 5, 6, because the model actually has to draw a whole bunch of decisions for every single fractional value. And so actually just telling it specifically, giving it a feature saying this is a decimal, ended up yielding decent value because it understood, okay, this value is 1.6, but 1.6 should be handled differently than 1 and 2. It's not necessarily exactly in between. And so I just share that example, not necessarily because you'll run into that too often, but it's another way to encode information and just think about, how do I provide something that the model isn't going to understand on its own? So a more common one that you'll likely run into is when the interaction between two variables are actually very important. So this is common in types of data where you have certain ratios that are actually valuable. So imagine someone has a loan, and you can look at their loan amount and you can infer something based on their loan amount, but actually the amount people have out on loans, it's also important to look at the ratio between the loan amount they have out and their income or various other factors. So you might look at outstanding loan divided by income or net worth or some other factor, and it ends up becoming a much more useful variable, because unnormalized like that without any denominator, it's much harder for it to pull anything predictive out of it. And that's something that the model can learn, but it will take way more splits if you don't actually represent that ratio. And that's something that is pretty common, that you'll find that if you know that there's some interaction between two variables, it's very very valuable, you should actually encode that yourself, because you can't guarantee that it will be picked up by the algorithm itself. So we're at time, and I've apparently timed it somewhat decently. So the takeaways: the gradient boosted decision trees are super powerful. There's lots of other stuff that has come out that we don't really have time to talk about today. So there's stuff like GrowNet and TabNet and neural network based systems that are starting to gain some traction and look like they're pretty successful, and may at some point overpass gradient boosted decision trees. But I would still err on the side of gradient boosted decision trees should be your default if you're doing tabular data. If you really have to eke as much performance as possible, it's definitely worth looking at those kinds of methods. But I would still say that currently gradient boosted decision trees are state of the art on this kind of problem. So one of the big things about gradient boosted decision trees is it can also simplify your process. If you don't have to fill in missing values, they can handle categorical values. They can do all kinds of different stuff just on their own that you don't have to handle with too much care. There's a lot of different parameters. In general, the defaults are actually pretty good, but you can definitely turn the few knobs that I pointed out, and you can almost always get additional performance out of that. But in general, you can run it and it will be robust and get you a decent solution. I've tried a whole bunch of this stuff from sklearn, and it's the case where you try with one, like the default hyperparameters, and then it just doesn't even fit to the data properly, and then you tune it a little bit and it will do a much better job. And that's not something that you see with the gradient boosted decision trees. Their defaults are actually pretty reasonable, and they'll be robust, and they'll give you decent results pretty much every time. And then the final thing is that the feature engineering and the transformations are still very important to get the best performance, but in general, you can pass the raw features into it and you will still get something that is fairly good, unless you have some secret hidden interaction that you don't have in there, or some representation that the model isn't able to find. So that's everything I have today. We can do some additional questions if anyone has any, but we're at time here.
So yeah, this is Venkat. I have a question. So how do you know in general whether the data has the expressive power to tell us regarding whether it can classify the label we are looking for? So what is like the test like?
I would say in general, the best litmus test is just doing the modeling. There's various different things that you can do. You can measure the correlation against the target and stuff like that. But the real test is always just doing the modeling and seeing how the performance is. That's the simplest way to check that, in my opinion.
Okay.
So I'm curious, with the boosted algorithms, I'm kind of on the fence on this. Do you do dimensionality reduction before, even though they will print out feature importance? I'm just curious if you take that extra step.
So I typically don't do dimensionality reduction. That's one of the options we have within driverless, actually, is there's a knob for interpretability. And if you turn the interpretability knob up, it will try to reduce the number of features that you're using. And sometimes it does that with various dimensionality reduction tricks. Sometimes it just does it by selecting out the features that are actually predictive. I don't typically do dimensionality reduction like that. Does that answer your question?
Oh yeah, sorry, I was on mute again.
Any other questions, comments?
So is this recorded where I can go back and watch? Where are the recording links posted?
They'll be put on YouTube, and then Ted also puts them on our GitHub, so that has the collection of all of the various talks and books and all of that stuff. So that the GitHub is probably the best place to look for that.
Okay.
I just pasted that into the chat.
Oh yeah, cool. Thank you.
So just give us a little bit of time to upload stuff. Cool. Thanks, Ryan. If there aren't further questions about this, let me just kind of throw it out to the crowd. Anybody have a different domain that they would vote for in terms of what you would like to see next? We did tabular. You want to see image classification? You want to see, you know, is there anything people want to vote for?
My vote would be for something like sound classification, like some of the Kaggle competitions, right? So
You got a time series in the chat.
Yeah, and image classification. So one for each. My hope is we'll keep going through and we'll interact with all of these different kinds. I think all of those are reasonable to interact with. So we'll do that at some point. Looks like lots for time series. We did, I did a talk on time series a long time ago, back when we were in person. So I'll have to dust all of that stuff off.
And then I'll just make a little bit of a plug. We've got a long way to go in the hands-on machine learning book. I mean, I think we're scheduled to go through March or something like that. But in the back of my mind, I am thinking about what we would talk about next. And I was wondering about maybe doing a time series book. And we could either do it in full, or we could go chapter by chapter, or like the reinforcement learning where we say, well, maybe we don't want to spend quite as long. We'll hit highlights, something like that.
Yeah. All right, we will tally up those votes and we'll have to figure out when and what to do next. But yeah, if no more questions, I think we'll wrap it up here. Thanks everyone for coming and participating and asking questions.
I have
Yeah,
a quick
thanks, Ryan.
question, please.
Yeah, go for it.
My question is PyTorch or TensorFlow paralyzed for language processing? Because I tried count vectorizer from scikit-learn and it is not paralyzed, to my regret. It took quite a lot to go through 2 million rows.
I've never done something like count vectorizer on TensorFlow or PyTorch. My concern with that is it already takes quite a bit of memory, and you might run into memory constraints with TensorFlow or PyTorch if you're doing it on GPU potentially. I'm not sure. I don't have experience.
But I wanted, yes, I did it for n-grams. Do you know some shorter way to find n-grams? Other method?
So you're trying to pull out the
Bigrams, trigrams, yes.
yeah. So you're
Yeah,
you're
so I think what Maya is saying is she just wants an implementation that does multiple workers and
Mhm.
and takes advantage of your cores.
Mhm.
But I don't know the answer off the top of my
Yeah,
head.
I'm not aware of any better implementation. I still use the scikit-learn one pretty much every time. So I don't know of any alternative.
I see. It is just, you know, when you look for bigrams and trigrams, then number of combination is much more than single words.
Yeah. Yeah.
Yeah.
Yeah, going up to 3 already makes it a massive array.
Yeah, Maya, I don't know if you see in the chat, Sule mentioned you could try using Dask. Dask will allow you to use multiple workers for otherwise not parallel workflow. What I just don't know is, depending on how they coded the underlying function, whether or not you will then, whether or not Dask will be able to split it out.
Yeah, that's a question, but I'll look it up. Dask, you know, does parallelization more natural than usual Python in scikit-learn in particular.
Yeah, but if it's
Thank you.
this giant black box, then Dask won't have access to it, and it won't parallelize anything.
Yeah.
All right. Well, thanks, Ryan. Thanks everyone for coming. But Ryan, thanks for giving us the tabular overview.
Yeah, no problem. Thanks everyone.
All right. Well, I hope everyone has a great Thanksgiving. We are off next Saturday, so no book club, no project discussion. If you come to this Zoom next week, you will be all by yourself. But so we resume in 2 weeks, and I believe oh, I can't remember. I think dimensionality reduction. Yes, I think Harold's doing dimensionality reduction. So 2 Saturdays from now. All right. Thanks, everyone.
Bye. Thank you, everyone.
Thank you. Bye. Happy Thanksgiving.